Hello, my name is Benjamin Lee. I'm part of the Research in Computational Science program at the North Carolina School of Science and Mathematics. And the project I worked on is an in silico study to enhance delivery efficiency of charged nasal spray aerosols to the olfactory region using external magnetic fields. For the treatment of neurological disorders like Alzheimer's disease or brain cancer, using drug delivery via the bloodstream, the blood-brain barrier is a major obstacle. However, one way to bypass the blood-brain barrier is through the olfactory region. By using nasal sprays to deliver drugs to the olfactory region, the drug can then pass to the brain. However, achieving efficient drug delivery to the olfactory region has been a challenge, and one way that has been studied to enhance drug delivery efficiency is using externally generated magnetic fields to guide the drug to the target region. So in this study, we applied a magnetic field to charged particles and also considered several other factors in order to find what parameters would result in enhanced efficiency. To simulate the drug delivery process, we used computational fluid dynamics and ANSYS Fluent software. A finite volume mesh was generated for the nasal airway, and nasal airflow was simulated using the Reynolds average Navier-Stokes equations. The airflow is modeled transiently, as the airflow rate was described by a realistic inhalation waveform. Also, the laminar to turbulent transitional flow was resolved using the four-equation transition SST turbulence model. Finally, a Lagrangian discrete phase model was used to calculate the trajectories of drug particles, including the effects of various forces such as drag and magnetic forces. The source of the magnetic field was a linear current-carrying wire, as shown in the figure on the top right, and this exerted force on the particles to draw them toward the front of the nasal cavity. We tested uniform injections, where particles were injected over the entire nostril, as well as targeted injections, with particles injected from specific positions. Several parameters were also modulated, including the size of the particles, the speed and angle at which particles were injected, the position of the nasal spray nozzle for targeted injections, which are shown in the bottom right figure, and the current through the wire, which relates to the strength of a magnetic field. For targeted injections, a spray cone was simulated, which had a constant spray angle of 30 degrees. First, uniform injections were tested, so the positions that particles were injected at were evenly distributed across the nasal inlets. The results showed that injection speed and angle did not have significant effects on delivery efficiency. For smaller nanoparticles, none of the magnetic fields for the range of currents tested had any major influence on the particle trajectories. Many of these particles traveled through the middle or bottom of the nasal cavity, as shown in the trajectories on the right. The particles tended to follow the streamlines of the nasal airflow, especially smaller particles, so mainly the particles injected at the front of the nostrils reached the upper nasal cavity. The charges of the particles were assumed to be proportional to their mass, so magnetic force per mass was equal regardless of particle size. For larger particles, certain levels of current resulted in around 3 to 4-fold increases in efficiency. Additionally, as particle size increased, the magnetic field strength needed to enhance the efficiency decreased. If the current was too high, the magnetic forces caused many particles to land on the front wall of the nasal cavity before reaching the olfactory region. Out of the uniform injection cases, 250 nanometer particles with 100,000 amps of current resulted in the highest efficiency, which was only slightly above 0.5%. Next, targeted injections were tested. For the uniform injections, all of the particles reaching the olfactory region originally were injected from the front of the nasal inlets, so I applied spray cone injections from the front of the inlets as well as from another adjusted position near the middle of the inlets. When particles were injected from the front of the nostrils, the efficiency increased significantly even without magnetic fields. Around 4% efficiency was achieved for the best cases, compared to uniform injections which had less than 1% efficiency. When magnetic fields were applied for initial targeted injections, stronger magnetic fields resulted in many particles depositing on the front wall of the nasal cavity before reaching the olfactory region. The adjusted positions, however, were moved slightly back from the initial targeted injections. With no magnetic field, no particles reached the olfactory region, but when magnetic fields of suitable strength for the particle size were applied, much higher efficiency was achieved. Compared to the initial targeted injection positions, less particles landed on the front wall, as the adjusted injection positions allowed for the magnetic field to draw particles toward the front of the nasal cavity and be more likely to deposit in the olfactory region without hitting the front wall of the nasal cavity before even reaching the olfactory region. Increasing the ejection angle by slanting the spray cone toward the back of the nasal cavity also contributed to higher deposition efficiency. As the injection angle increased from -30° from the vertical to 75° from the vertical, the deposition efficiency increased. With the magnetic field and targeted injection from the adjusted position, the highest efficiency achieved was around 11%. The results show an interesting relationship between particle diameter and the suitable magnetic field strengths to direct particles such that more deposit in the olfactory region. This is likely due to drag, since larger particles experience less drag force per mass. This explains why the larger nanoparticles needed lower levels of current to influence their trajectories and increase the deposition efficiency compared to smaller particles. The study also provides insight on how various drug delivery parameters can be integrated. While some cases might include magnetic fields not feasible for physical tests, this study suggests the external forces that are suitable to increase delivery efficiency. When certain forces are applied, and these are combined with targeted injections with suitable position and angle, olfactory delivery efficiency can be significantly enhanced. Compared to control cases with uniform injections and no magnetic field, the best efficiencies achieved were over 65 times greater. Delivering the drug to the target region is the first step and a very important part in the process of being able to treat neurological disorders via the olfactory pathway. Thank you to the NCSSM Research and Computational Science program and my teacher, Mr. Gottwals. I would also like to thank the ANSYS CVBL partnership and High Performance Computing Center at Oklahoma State University for access to ANSYS software. Thank you for watching.